Okay, let's dive right into this. Welcome, Grade 7 learners, to our explainer for Information Technology, Unit 6, Lesson 2. Today, we're looking at something incredibly powerful, problem solving and computational thinking. If you've ever wondered how developers create massive video games, or design life-saving apps, or build these crazy systems that connect the whole globe, well, you're in the exact right place. We're going to uncover the precise thought process they use to pull it all off. So here's our quick mental roadmap for today. We're using these 5 pillars as our blueprint, starting off with the problem-solving mindset, moving on to decomposition, pattern recognition, algorithms and pseudocode, and finally, testing and refining. Let's jump straight into Section 1, the problem-solving mindset. Before we even think about writing a single line of code, we really have to prepare ourselves to look at the world a little bit differently. And it all starts with one really big question. How do computers actually solve incredibly complex problems? When we're scrolling on a smartphone or typing on a laptop, it's so easy to fall into the trap of thinking that computers are just magically smart. But actually, scratch that. They aren't smart on their own at all. They rely entirely on human-designed problem-solving frameworks. A computer literally only does exactly what a human tells it to do. So how do we tell them what to do when the problem is just huge? The secret sauce? It's called computational thinking. This is your ultimate blueprint for building solutions in the digital world. It's a highly specific problem-solving process. Notice the 4 main actions at play here: breaking down complex problems, recognizing patterns, designing algorithms, and refining solutions. You see, this isn't just about computers. This is a whole new way of organizing your thoughts so that a computer can eventually execute them. All right, moving on to Section 2, decomposition, breaking it down. Decomposition is the very first major pillar in our computational thinking framework, and it's all about taking massive, overwhelming tasks and making them totally manageable. Think about a simple process. Get user input, process the data, and display the result to the user. That right there, that's decomposition in action. The standard process tells us we should break down big problems into smaller subproblems, which we can then break down into even smaller parts. By focusing on just one piece at a time, like, say, just getting the input from the user, the whole project suddenly becomes way less scary. Imagine you're programming an animation. Instead of trying to code the entire movie all at once, you decompose it. You separate the story into different, completely independent scenes. You pick a background, place your characters, program their actions just scene by scene. It's so efficient that it even allows different students to work on different parts at the exact same time. Now for Section 3, data and pattern recognition. Once we've broken our big problem down into manageable chunks, we need to start organizing the information we have so we can spot clear relationships. It's honestly amazing to watch how raw data gets transformed into something genuinely useful. Let's say we're trying to predict how far a ball is going to travel on a track. On its own, a bunch of random measurements, they don't help us much. But when we organize that information side by side, comparing the track height, the track angle, and the actual distance the ball traveled, patterns start to emerge. We can clearly see that as the track height and angle increase, the distance traveled also increases. By organizing our data like this, we expose these cause and effect relationships, and this allows us to abstract the really important rules and refine our computational models based on actual generated data. We test our predictions against the real results, and we might even realize, hey, we need more data points, like the size and mass of the ball, to make our model perfect. Which brings us to Section 4, algorithms and pseudocode. So now that we've found the hidden patterns in our data, we absolutely need a way to turn them into clear step-by-step instructions. Computers crave structure. Imagine a totally chaotic real-world process, like trying to find the perfect pair of shoes by digging through a giant, disorganized pile. It is frustrating, right? Totally inefficient. But the computational solution to that mess is an algorithm. An algorithm is literally just a set of step-by-step instructions. But before we dive into writing actual code, we use something called pseudocode. Think of it as a way to organize our logic using everyday language just mixed with a little bit of programming structure. For example, we might write a pseudocode algorithm that gives us a sneaker recommendation based on specific inputs. We'd filter by size, then filter by colors, then brand, comfort, and finally cost. It takes a messy, chaotic problem and gives it a highly structured sequence that a computer can easily follow. And finally, Section 5. Testing and refining solutions. You've written your pseudocode, you've designed a brilliant algorithm, but you know what? You're not quite done yet. This is the final, absolutely critical step of our blueprint. We must systematically test and debug our programs. Think about it. What actually happens if a user enters a negative number instead of a positive one? Or what if they just enter a 0? This is exactly why testing is essential. At this level, testing isn't just about frantically fixing things when they completely crash. It becomes a deliberate, systematic, and proactive process. We have to create what are called test cases. We literally try to break our own programs by throwing in invalid inputs just to see how the system reacts. If our algorithm is supposed to calculate the cost of some sneakers, a negative number would cause a major bug. So we test these cases to refine our solution, identify any inputs we might have missed, and ensure the final program perfectly meets the user's needs. Let's wrap up this mental roadmap. Here are the core pillars of the unit we've just explored together. We kicked things off with decomposition, learning how to break complex problems down into smaller, independent subproblems. Then we looked at abstraction and patterns, figuring out how to organize our data to expose hidden relationships and pull out the most important rules. Next, we learned about algorithms, taking those patterns and writing clear, step-by-step instructions using pseudocode. And finally, refinement, which is that proactive process of testing our programs with a wide range of test cases to debug and perfect our work. That right there is the full cycle of computational thinking. I want to leave you with a final, slightly provocative thought. We've talked about animations, balls rolling on tracks, and buying sneakers, but how can you apply these exact 4 computational thinking steps to solve a real problem in your own community? Maybe you could build an app that connects people to local volunteer opportunities, or even a system to track recycling in your neighborhood. You now have the exact blueprint that professional software engineers use every single day. The next step is entirely yours. Look around, find a problem, break it down, and start building your own incredible solutions.